so that we actually are recording this. Okay, so we're looking for associations. We're looking for associations between two variables. In this case, when we're dealing with correlation, we're looking for associations between numerical variables. Each one of these lines, these rows going across, represents an individual. And we've measured two variables for that individual, both numerical variables. One is age, and the other one is blood sugar in this case. Okay, so we want to know whether there's an association between a person's age and their blood sugar. Obviously, this data is fabricated. Could have been many other things that we looked at. In this case, we're just looking at age and blood sugar, and we're using this data to give you an example of how we might handle this numerically. In our heads, we say to ourselves, oh, correlation between age and blood sugar kind of makes sense. Get older, you're diabetic, your blood sugar goes up. And so it wouldn't be that surprising to see, well, this young guy, he might have lower blood sugar than this older guy. So you can kind of wrap your head around it. As I said, in statistics, though, we're actually going to look at this numerically. The first way I might want to look at this to get an idea of whether or not there's some association between the first variable, whatever it happens to be, and the second variable is to look at it from the perspective of what does it look like graphically. In other words, I have age, blood sugar for each person. Let's say that this is an X value on a graph, and this is a Y value on a graph. So age 30, blood sugar 75, that would represent the X and Y coordinates of a point or a dot on a graph. So I'm actually going to go ahead and graph that. Hopefully, I actually might even have this as a table already. If not, I'm just going to copy it. I thought I had it. Guess I don't have it. Okay, that's okay. Okay, I'm going to open up SPSS. You guys might want to do the same thing. Okay, and I'm going to do something really novel for us in SPSS. I'm just going to type the data in. You know, I'm not even going to bother opening another file or anything like that. It's only 20 numbers. This is going to be our first example of actually just using SPSS raw and entering data in it from scratch. Now mine is about to expire at the end of the month, so instead of letting me be what actually expired last month, but fortunately they took pity on me and they let me open it with that warning, but they force me to wait a little while, and each time I open it, I have to wait a little longer. So kind of annoying, right? But I mean, that's the price you pay. Let me see what I can. Maybe I can do another operation and get it to give me the opportunity to open this. Come on. Let me see if I do that. Here we go. Now let me do it. Okay, I'm going to say open. And I'm going to start with a new data sheet. Actually, I have one open behind me. I could have just said new data. It would open in a new window. But I have a blank window behind me. And I'm actually going to enter this data into this window. I'm going to start with age. I'm going to say, okay, age is 30. Next person is 34. Next person is 36. Next person is 38. So if you have data that you have that's not formatted for SPSS, and a few people have mentioned that you do have data like that, you actually you can enter it into Excel and import it, or you can actually just type it into SPSS. So I have 10 people here. Hopefully when I get to the 60, it'll be 10 people, and I got that right. And my other variable, notice since I didn't give it a variable name, that it filled in a fake variable name, VAR 00001. Okay, and it's going to do the same thing for the next column. I can fix that in a moment. Okay, and then I'm going to put in the blood sugars. 75, 90, 65. I'm using the down arrow as I enter it. 85, 110, 80, 103, 110 again, 115, 140. And we can kind of look at this data and see, well, As age goes up, it just happens that the age column is sorted by age. As age goes up, in general, I'm seeing higher numbers for blood sugar as I go up. I'm going to go into the variable view. How about 29 pages worth? How about 2,000 individual data points? Well, in that case, we have to find a way to avoid having to do all of that. And we can do various tricks with Word, with Excel, with other tools to maybe try and ferret out that data. And if we have to, maybe in some cases, we might actually just take a subset of that, like randomly select 200 or 100 individuals out of those 2,000 and work with them instead, at least for the purposes of your project. So I'm going to go into the variable view. Now, the first column was age. So I'm going to change that variable name to age. And the second column, I'm going to double click on that. Second column was blood sugar. So I'm just going to type BS for blood sugar in there. Now, those the variable names in SPSS have to start with a letter. They can only have a certain length. They can have letter after that first letter. They can have letters or numbers. They can't have any special characters. No dollar signs, no underscores, so on and so forth. And they have a limited length, as I mentioned. Okay, so they can't be. They're not going to be very, and no spaces, right? So they can't be very descriptive. So if we were going to produce tables and graphs, we don't want it to show age and BS and so on and so forth, because it's going to be hard for people that don't know what the origin of these tables were. It's going to be hard for them to understand what this information is. So we have another column over here where we can type into label a more complete normal description, English description. So this is age of patient, let's say. And this is the blood sugar for the patient. Okay, you might chase that with the units. What are the units for blood sugar? Milligrams per deciliter, milligrams per deciliter. Okay, milligrams per deciliter. Let's say. Oops. Okay, whatever they are. So when that shows up on the graph, it's going to be a much more descriptive way of presenting the data, and it'll save you the trouble of having to modify the graph to make it understandable. So I'm going to go back to my data view. Now this is numerical data. Again, each one of these are going to be a data point. So I'm going to want to graph this. So I'm going to go in here. I'm going to go up to graphs. I'm going to use the simplest version of this. Yeah, it did something behind me, right? Okay, they don't see this at home. They don't know what's happening here. Oh, that's me. Okay, so I'm going to go in here, go to Legacy Dialogues. I'm going to go down to Scatter Dot. Okay, and you can see each one, it's just going to plot the various data points as X and Y coordinates. I'm going to say define. Now, it doesn't matter for correlation whether I put the blood sugar or the age of the patient into the y-axis or the x-axis. Later on, when we discuss regression, it's going to matter. Right now, it's not going to matter because we're not interested in whether blood sugar causes somebody to get old, or whether somebody getting old causes blood sugar to change. We don't care about this. We just want to see if there's an association. So it doesn't matter which one I put in where. So I'm going to put the age of the patient. Sounds reasonable for me to put that into the x-axis, but it doesn't matter. It's not going to affect our calculations. I'm going to put in blood sugar into the y-axis. And I'm going to say, I'm just going to click it OK. I'm not going to bother with titles or anything like that. And it's going to plot it for me. I could have done this, just with a piece of paper if I wanted to. Now, what do we see? We see as the age of the patient goes up, we see that in general, we're seeing a pattern here. It's sloping upwards. Blood sugar is going up also. It appears to us there's a correlation or an association between age and blood sugar. I'm going to do it the other way just so you can see that it's not going to make a difference in the graph. I'm going to see, analyze, or in our calculation. Scatter dot, I'm going to do it again, except this time I'm going to reverse them. Okay, it may be a little less meaningful in some ways to do it the other way, because we're used to looking for the independent variable, the causative variable on the x-axis and the result on the y. So it's makes a little less sense to us. But if you look at it, it's still sloping upwards, and we can still see a pattern. Right? A little bit different shape, but but we still see that the association is there. When we do calculations to measure that association, we're actually going to see more. We're actually going to quantify it. It's going to be the same, whichever one we define as the x or the y. I'm going to double click on this, and when I double click on it, it brings up a chart editor. One of the things the chart editor allows me to do is to add a line that will basically give me my correlation line. This line is an approximation of where all these data points are. In other words, it's drawn so that if we were to add up all of the distances on one side of the line to the points, they're balanced by the distances to the ones on the other side of the line. Actually, if you look at the formulas that Levi was going through, it's actually the sum of the squares of these distances rather than the distances themselves. Okay, so when I look at this, this line approximates this relationship. The slope of this line gives us an idea of how much of an impact age has on blood sugar and so on. So that's of some interest to us. However, when we do correlation, we want to quantify this. We want to know how sure are we that this is really a real correlation and not just, we only sample 10 people. Okay, so we're going to actually go in here and do an actual calculation. So I'm going to go into Analyze. I'm going to go into, well, look, we got a selection for it, correlation. And I'm going to choose bivariate correlation because bivariate means two variables. Okay, and just as we did before, we're going to move the two variables into the box on the right. Now, as soon as I get the second variable in there, the OK box lights up because it's ready for me to do the analysis. Notice that it doesn't care. It's not like before when we're doing like factor and dependent variable. It doesn't care because the numbers are just going to be the numbers. It doesn't care about the association or which one causes the other and so on and so forth. When we're doing correlation, all we care about is whether or not there is an association. Okay, I'm going to click OK. Happens to be called Pearson's correlation. Again, Pearson gets around, right? Okay, and if I take a look at this, I see a couple of boxes here. In its usual fashion, SPSS kind of doubles the output. It compares the age of the patient, right, to the age of the patient. Well, that's a perfect correlation, right? Age of the patient, the age of the patient, that's the same number for each patient. 30-year-old, his age is 30, and you associate it with his age is 30, it's 30 is 30. That correlation is 1. Any correlation that's perfect, where there's an exact relationship between one variable and the other, then that's going to be a correlation of 1. Okay. Any association where any correlation where there's no association. In other words, instead of getting a nice kind of linear look to this, at least somewhat linear look to this, all you get is a cloud. Like it doesn't seem like there's any association between what's on the x-axis and the y-axis. It just seems random. That would be a correlation of 0. You would get 0 for the Pearson's correlation. So if I look at this, anything that I get that's close to a 0 suggests a poor association, a poor correlation. Anything that's close to 1 suggests a good association. It even goes a little further than that. The reason why we see positive numbers here is because we're doing, the slope is positive. As one gets larger, the other gets larger too. If it turned out that as age went up, blood sugar went down, that would be we'd get a slope, negative slope, then we would get negative correlations, a negative number. A -1 or a +1 is a perfect positive correlation or a perfect negative correlation. A 0 is no correlation at all. So we're looking for something close to 1. So if I look at this, the age of the patient, right? When I associate that with the blood sugar, the correlation, the Pearson's correlation, is 0.821. Does that sound like a good correlation? Sure does. It's close to 1, right? If we're 0.5, it'd be pretty good. If we're 0.4, it'd still be pretty good, right? So that gives us an idea of how good the correlation is, how good the agreement is. There is also a significance. This tells us how statistically significant correlation is. In other words, this tells us that it's less than 5% chance that this correlation is not 0, is not 0. In other words, our null hypothesis is like everything else, that there's no association, that the correlation is zero. This tells us that we can reject that idea and say that there is a correlation. It might be a poor one like 0.2, or it might be a good one like 0.8. In this case, it's a good one. So this gives us an idea that there's an association. Now, does that mean that one causes the other? Any opinions? I think in the lecture, Levi mentioned just because you got correlation doesn't mean that there's causality. It just means that there's an association. I'm going to give you an example of one right now. Let me see if I can't find it. Okay. Okay, I'm going to do the same thing with this other data set. Okay. I'll show it to you in an Excel file first. Okay, I didn't say what the variables were here, but these are actually different years. That's year 1, year 2, year 3, year 4. And this, as one goes up, as this one goes up, seems like the other one goes up as well, right? Gets larger as well. Okay, it varies around. I'm going to actually use SPSS. This is the same data typed into SPSS. I'm going to produce a scatter plot. Okay, I'm going to put one variable in here, one variable in there. It doesn't matter which one I choose. It's a correlation. Okay, and I'm going to take a look at my scatter plot. Look, that's a pretty damn good correlation, isn't it? Okay, and let me see. Let me do an analysis. Analyze, correlate, bivariate. And I'm going to put both of those in there and do a correlation. The correlation is remarkably, look at that significance. The p-value is less than 1/10 of 1%. The correlation is almost perfect, 0.94. Right? Great correlation between these two sets of numbers. Let me show you what these two sets of numbers are. I'll open an article that went along with this data. Let's see. See if I got the right one there. Here it is. The more people eat cheese, the more people are killed by their bed sheets. This shows that one number is the per capita consumption of cheese for each of a different number of years, and the other number is the number of people that get strangled in their own bed sheets each year, right? So now, do you think how much cheese is eaten in a country has any actual impact on the people? Right? That's a spurious correlation. It's a remarkable coincidence, right? But the reason why this article came up, and the reason why I know this, is because there's a statistician that has made a hobby out of collecting these spurious associations, and that's one of the ones that he happened to find. Here's a year by year analysis, the two numerical variables: U.S. spending on science, space, and technologies, and suicides by hanging, strangulation, and suffocation. Here's another one: number of people drowned by falling into a swimming pool correlates with the number of films Nicolas Cage. Now look at these associations; they're unbelievable, aren't they? Right? And think of how many people. And there's our cheese association right there. He plots it differently. He plots it as year by year level on two tables. This one is the number of pounds of cheese, and this is the and so on and so forth. So he's got lots of these. So that should let you know. Another example might be if you were to plot the number of firemen that go to a fire and the amount of damage that's caused by a fire, right? You would think that, gee, more firemen, you have more damage there is, right? But we know that it's a spurious association. The real story there is the bigger fire is, the more firemen you send, right? So that's why that really happens. But you could, if you're not careful, you can wind up thinking firemen are causing the extra damage, right? Not that they don't sometimes. I've seen them work. But at any rate, that's a whole other thing. But so I'll post that link so you can get a look at it. It's pretty interesting stuff. Okay, so we have to be a little bit cautious about this, especially because our next step is to actually try and use this information to develop it into a tool that'll help us make predictions, to help us better understand how one factor influences, one variable influences another variable. So I just want to go through this, make sure I haven't missed anything here. This document will step you through how to do these analyses using SPSS. I just want to check online to see if there's any questions. Do you guys have any questions? Can you still hear me online there? Somebody type something in so I know you're there. Oh, good. Thank you. All right. Pretty interesting stuff so far, right? Now, and one of the interesting things about this is that up until this point, we haven't had a tool to compare numerical data and numerical data. For instance, if we use t-tests to compare categorical and numerical data. In other words, if we measured the blood sugar of one group and the blood sugar of another group, we would find the average blood sugars of each group and compare them, right? That's a t-test. We wouldn't be directly comparing individual to individual. If we were if we were working with categorical variables, in other words, if we were working with one of the examples we had was IV drug use, yes or no, and HIV status, yes or no, a positive or negative. Okay, in that example, we're dealing with two categorical variables. Each one of them has a value of 1 or 2, and we were looking to see if there's some association. So we used chi-square. If it was a 2 by 2 table or bigger that we wound up, we'd use chi-square. If it was a 2 by 2 table, we could use chi-square, or we could also use odds ratio or relative risk, which work with 2 by 2 tables. Now we have a way to evaluate and examine whether there's a relationship between two numerical variables. So if you have data, for instance, that you know what the person's BMI, you have 100 individuals and you know what their BMI is. That's a number. And you want to see if their BMI is associated with their heart rate on exercising for a certain period of time. You would have one variable is the BMI, which is numerical. The other variable is their increase of their pulse rate on exercising. And you may want to say, well, maybe the higher BMI you are, the larger the increase in pulse rate is when you exercise from when you were resting. And you want to compare those two. And now you have a mechanism to compare two numerical variables, right? You can find out if you can plot them as a scatter plot, and you can examine the data, and you can attempt to see if there's a correlation. Next thing you want to do is, gee, I want to see, I want to examine this I want to research this. I want to see if there's an argument for saying that there is an association for BMI and increase in pulse rate on exercising. Then you research it for a bit. You find some evidence that physiologically there's an argument for it. You find maybe other studies that maybe have examined it and so on and so forth. Well, once you have an idea that, gee, I really think there's a pretty good chance that BMI, and there is a correlation, but I have an idea that it's causal. BMI actually does influence someone's increase in pulse rate performing a certain measured exercise. So now you want to be able to use that information. Now we're going to go on to the next part. The next part is called regression. And in the regression analysis, what we try and do is take those two variables and determine mathematically what is the relationship between the two of them in terms of an equation. Well, we got two variables, we got a point, and we drew a line which represented what we thought would be the best fit for a straight line between the values that we had before. Now we're going to take a little closer look at that line. We're going to want to see if that line, what the slope of that line is, and what the formula for that line might be. So I'm going to go back to SPSS, to the evaluation that we were just doing before. Here we go. I'll open my output window again. If I still got it, I think I still got it. There it is. Okay, here's my output window. There's my scatter dot plot, and there's my my line, which represents the best fit for a straight line. Well, you guys remember back from algebra that there's a couple of ways for you to define a straight line. One way is that you find 2 points on the straight line, and it defines the straight line. If you know 2 points on a straight line, you know that straight line. Because once you draw a straight line, it can't go anywhere else. It's got to match to fit those 2 points, right? So I only have 1 point that really looks like it's on here. But there's another way that I can define a straight line, and that is I can describe its slope. Right? And what's the slope? The slope is the change in x over the change in change in y over the change in x, right? The change in y, the height, over the change in x. So you would pick 2 points, one here, one somewhere else, and see how much it changed going upwards in the y direction or downwards, for that matter. That'd be a negative slope, and how much it changed in the x direction. The other thing I need besides slope is I need to know some anchor point. In other words, I know the slope, but it could be that slope could be here or it could be here. It's the same slope over here or the same slope over here. I need an anchor point. That anchor point usually is the y-intercept. The y-intercept is the place where that line crosses 0 on the x-axis. In other words, where it crosses the y-axis. Well, on this particular graph, you can't see it here because this is 3530. It would be we'd have to follow it way down here, and we'd cross it down here somewhere. Might even be a number that really makes sense because nobody's going to have a 0 blood sugar or a negative blood sugar, but it's at least going to be a number which tells us that we can define a line that way. Okay, so what I'm going to do now is I'm just going to pull something up here so you can see what I'm talking about. Let me get to the notebook. Okay. Okay, and I'm going to just draw something here. Okay, here is my y-axis. Here's my x-axis. So if this is 0, 10, 20, 30, and this is 10, 20, 30. Well, let's say I have something, a line that looks something like this. Okay, I can define its formula by y is equal to mx plus b. I hate to say this, but I always remember this formula. Going back to high school, that's how I learned to write the formula in high school. Unfortunately, it's not the way statisticians write the formula. They write it as f of x or y is equal to, and I'm going to take a wild guess here, a plus bx. Do I have that right, or is it b plus ax? Doesn't really matter, right? Okay. I'm sorry, say it again. Which one we use? Let's see what your book says. Oh, beta x plus, okay, alpha plus beta x. Okay, alpha plus beta x. Okay, all right, that's what's in Pearson's? I mean, in Agresti? Oh, in the lecture, okay. I think Agresti's uses A and B, right? So alpha plus beta x is good enough, right? Because if you look at it here, it's the same thing I'm doing, except mine would be y is equal to b plus mx, right? So beta is the slope, alpha is where it crosses the y-intercept. How do I know alpha is where it crosses the y-intercept? Well, when x is 0, that's the y-axis, right? When x is 0. When x is 0, 0 times beta is 0. So all you're left with is alpha, where it crosses the y-intercept, right? So the formula for this line in particular would be, well, let me take a look at it. If I go over at 0, it looks like it's about 8, right? And if I go up to, say, 20, it looks like it's about, I'm going to say 16, right? So the change in y over the change in x is about 8 over 20, right? Or is about 0.4, 0.4. Okay, so y is equal to, well, the y-intercept is 8 plus 0.4 plus 0.4 times x. That line, this formula, describes any point on this straight line. If I wanted to know what y was equal to at 30, all I'd have to do is say y is equal to 8 plus 0.4 times 30, right, which is 12, I guess, is equal to 8 plus 12 is equal to y is 20. So this point would be 20 comma 30. And in fact, actually, by some accident, it actually kind of looks like that. Okay, so this formula defines this relationship for me. Okay, now I'm going to do the same thing with our data. I'm going to develop a formula using SPSS that defines the relationship for us between age and blood sugar, or the bogus relationship as it happens, because it's really, it's not really true. No. Okay, so I'm going to go back to our data. Here's our data. And I'm going to go in here and I'm going to analyze. And this time, instead of going to correlation, I'm going to go to regression. And it doesn't say bivariate yet. Instead, it just says linear. I'm going to choose linear regression. In other words, a regression involving a straight line. This time, you want to know something? I'm looking at the wrong one. I want to reopen my data. Where'd it go? For age. Did I erase it? Did I close it? I don't think I did. It would have warned me. Nope, that's not it. I think I must have erased it, no? Is that what happened? Tell me I didn't do that. That's not here anymore, so I must have erased it. Okay, I'm going to have to type it in again, unfortunately. I can't believe I did that. Okay, maybe I can shortcut this a little bit. Let me go into this Word file. Oh, it's a PDF file, unfortunately. I don't think this will work. Let me see if I can't do this. Let me see if I can't get away with this. Copy. Excel. Oh, what do you know? Okay, I'm going to insert a row here. And I'm going to put age and blood sugar. Hopefully you guys kept yours open. Or saved it at least. I need to quit that. Now, just so you know, SPSS will not tolerate having a data file opened by another program if you try to import it. New data. I'm going to go to the desktop. Whoops. New, open data. I'm going to go to the desktop. I'm going to look for Excel files. And the Excel file I'm interested in is, what did I just call that file? Mass Association. I forgot what I called the file. Let's try this one, see if that imports. Nope, that's the wrong one. Oh, data, I called it. Okay. Okay, open, data, desktop, data. There it is, except I can't get it because I'm only looking for SPSS files. Change it to Excel. Now I can import this. A1 to B11. Notice that there's a little checkbox here. Read variable name from the first row of data. I put the variable name on the first row of data, so I want to leave that checked. Okay, it imports it, and now I have it in my variables. I just want to go back here and relabel it. Age of the patient and blood sugar. Just so it makes sense when I do the analysis. Okay, so now this time I'm going to go to Analyze. I'm going to go to Regression. I'm going to go to Linear. And this time, instead of having one box to move the variables into, I have two boxes to move the variables into. I have two boxes because one is dependent on the other. Now I have to tell SPSS what I believe is the causative variable and what I believe is the result variable. Okay, the independent variable is the one that causes the value of the dependent variable. So what do we think the independent variable is here? Is it age or blood sugar? Age. So we're going to move age into independent, and that'll mean we're going to move blood sugar level into dependent. Okay, so now I have a whole bunch of options here and so on and so forth. For the most part, I'm going to stay away from that for now. And I'm just going to click OK. Okay, SPSS now does a complete analysis. One of the things it does is it repeats our correlation analysis. Okay, and if you look up here, the correlation is 0.821. You guys remember that, right? That R value, that R represents the Pearson's correlation. It also takes that number and it squares it. And it's 0.67 in this case, right? Squared to 0.81. That's where I got that 0.67. That R square variable is important to us. I'll come back to that in a minute. We're going to be interested in that. And then it does an analysis of variance. Remember, Professor Waldron mentioned that the basis for the math here is basically the same math that we use for analysis of variance. I don't expect you guys to wrap your heads around that, in the short period of time that we have to play with this. But basically, it tells us that there's a very small chance that this regression or this correlation is by chance, less than 5% chance that it's by chance. Okay, so now I'm going to go down here to this last box. This last box gives us coefficients, the alpha and the beta that we need to work with in order to define our line. And it says that the constant, that's our, what is that going to be? That's our y-intercept. That constant is, or y-intercept is 14.47. In other words, when the age is 0, the blood sugar, remember I told you it probably doesn't make any sense. It could even be a negative number. And age 0 doesn't make any sense either. But when it's 0, it's the line crosses the y-axis at 17.47. Okay, now correlations and regressions only make sense within the range that you have actual data. In other words, you really don't pay attention to, like where that line goes, to infinity. And you don't pay attention to where that line goes to nothing, right? You just pay attention to it really in the reasonable areas where it's applicable, like in the human areas, right? So this 1.7 represents our slope for that line, okay? For every change in every change of 1 in the x value, that's 1 year of age, there's a change of 1.7 in the blood sugar. That's what the slope of this line represents. So I actually can write this formula out now. I can go back to my notepad. Okay, and now this formula becomes, whoops, let me make a new page here. Okay, our formula again was y is equal to alpha plus beta x, right? Well, y is equal to, well, alpha turned out to be, the y-intercept was 17, I'm going to call it 17.5. Plus beta, I'm going to call that 1.8 for our purposes, times x. So now this formula, I can use this formula to predict y. Now, why might that be useful? Well, this is kind of a trite example. It really isn't a very good example of this. But if I have a new patient that comes in, and this patient is, I don't know, let's say he's 55 years old, right? I say to myself, well, I'm going to figure this out using this formula. 17.5 plus 1.8 times his age, which is 55. Well, that's going to be, let me get my calculator out. I'm going to say 1.8 times 55 is equal to this, plus 17.5 equals 116.5. 116.5. What I'm saying is that, based on the data that I have, my expectation is that this 55-year-old is going to have a blood sugar, maybe it's non-fasting, let's say, a non-fasting blood sugar of 116. If it's much higher or lower than that, that might alarm me, right? Or since he's 55, I say to myself, it's a good shot this guy's, like is pre-diabetic or diabetic. If I go to a doctor now my age, they look at me and they say, you're pre-diabetic. Don't laugh. It's the truth. Like I have friends, they walk into the doctor, they get a fasting blood sugar like 90, and they tell them you're pre-diabetic. If the guy had the same blood sugar and he was 22, they wouldn't have said a word. Am I wrong about this, or it's the truth? Everybody walks into a doctor's office is pre-diabetic if you're over 50. That's it. It's a given. But at any rate, but yeah, I know some of the other nurses know this. The doctors are all doing. They all some paper comes out, or they must all subscribe to some email list or something like that, because they all do the same thing at the same time. And they change direction. Like, you ever see fish in the ocean, like in a school, and then all of a sudden they change direction, and every one of them goes. They all do that too. They're just like a school of fish. But at any rate, that's neither here nor there. This. What's that? It really does get your attention. I had like a cousin that's down in Florida. She just turned 50, and she went to a doctor. The doctor told her you're pre-diabetic. For almost 3 weeks, she was eating nothing but fruit. Then forget it. That was done. She forgot about it, and she's back to her old diet. But anyway, that's all. She was on Facebook every day talking about her diet. But now I don't hear. All I see is her cat. So her diet's over with, I guess. But at any rate, it got her going for 3 weeks. But at any rate, that seems to be a real thing now, pre-diabetic. But at any rate, so we can use this as a predictor. We can use this as a tool now. We can use this in a lot of other ways as well. So this formula now is valuable to us. There's also another way that we can use this. We can actually evaluate several variables in relationship to blood sugar. For instance, we can look at how does BMI affect blood sugar. We can look at, besides age and BMI, how does level of physical activity affect blood sugar? How does this other stuff affect blood sugar? And the interesting thing is that we can make graphs for this. And those graphs, each one of those graphs is going to have a different slope, right? And you can take a look at that slope and you can say to yourself, if I bring somebody's BMI down, it has, the slope is very slow. Maybe it doesn't have that much of an influence. They really have to lose a lot of weight to make a difference. But if I make him exercise a little bit more, that slope is much steeper. So a little bit more exercise may be a better, more effective control than reducing weight. So in other words, you can start to make evaluations. These are called multiple regressions. You can actually build a formula that instead of having alpha plus beta x, has alpha plus beta x plus beta 1 x1 plus beta x2, and that's called a multiple regression. You can look at this, many variables at the same time, and all of them add together to give you a better predictor of the outcome. Yes?
In the lecture, you mentioned that having too many variables, and you could almost get too good of a fit where you can't use that interpretation outside of your own.
Right.
Yeah. How do you decide how many is too many?
That's a good quote. I hate to say it, but multiple regression is a little bit beyond what we're doing. And there are courses. In other words, you wouldn't just take one course. You take you wouldn't take one lecture. You take an entire course on regression and multiple regression, logistic regression, a whole bunch of series of ways to use these techniques to evaluate data. So, I'm not sure how you would decide, when you've gone too far. As far as a predictor is. But the point is that you get to examine many variables at the same time and see their influence on what you're trying to control on the output. So you can decide, well, my money or my energies are best spent controlling this because it's going to have the most might be most effective at controlling my result variable, whatever that happens to be. Okay, so I'm going to take a look at a couple more of these things. And now just want to show you before I go any further, you may have noticed that that formula also has a little tail on it, which is kind of an epsilon, right? Plus, right, that little e kind of like that, right? It's saying that, oh, but for each individual, this is our predictor, this is our straight line that we're trying to fit. But for each individual, you're going to miss it by a little bit. Remember when we saw that graph, when we saw the straight line on that graph? There literally was no individual, except maybe this guy right here, came close. But even that one, I can't get it to enlarge. Even that one is not right on the line. So none of these actually lands on our line, is exactly predicted by our formula. However, it's a pretty good tool, this formula, in predicting what you would expect the outcome variable to be, nonetheless. But every one of these has a certain error involved in it. That's called a residual. You can actually use, so the residual would be, is that for this any particular individual, right? Like this person that's 38. For that person that's 38, what would his actual blood sugar was 85. What would our model have predicted? I can actually use SPSS to do that. Okay, okay, I'm going to go here. I'm going to say analyze. I'm going to say, let's see. Where do I find this again? I'm trying to remember where I'm going to regression, linear. I'm going to go into save, this little button here called save. And I'm going to say, show me my predicted values and show me my unstandardized residuals. Unstandardized means show me the actual number. A lot of times, like in a lot of statistics, we're not interested in the actual number. We're only interested in how many standard deviations away from the mean that it is. And if I wanted that, I would check standardized, but I want the actual number. I'm going to click continue. Then I'm going to click OK. It does the analysis again. We didn't need it, did the analysis again anyway. But it added two variables that we didn't have before. This is our predicted value, and this is our residual. In other words, based on that formula, that person that was 38, his blood sugar was actually 85. We predicted using our formula that was 84. That happened to be the guy that was almost on that line. Our residual is only half, right? But if I took a look at this person that's 52, right? His blood sugar was 103. We predicted it was going to be 109. So our residual is, we have an error of -6, right? We're 6 over. We got to subtract 6 from our predicted value to get the real value. So one of the things that we do is look at these residual values and see how extreme they are, and try to make sure that they're randomly distributed, that they're not all at the low end, and the big errors at the low end, small errors at the high end, that there's no pattern to it, that